Hello everyone. So today is the second part of lecture number 4 about footing design. So this week we will be talking about footing design part 1 about shallow foundation or shallow footing. Under shallow footing we have two topics. The first topic is design of shallow foundation or shallow footing based on bearing capacity. The second topic will be design of shallow footing based on soil reactivity. So, first of all, what is the difference between foundation and footing? Foundation of a structure means the ground on which it's supported. So, if we have a structure, so the foundation is the ground underneath the structure. The structure loads are transferred to the ground via footing. Footing is the system that transfers the load to the ground. So in some cases or in some countries, footing are very close meaning to the foundation. But here, foundation is considered the ground and footing is considered the structure system that transfers the load to the ground. Okay, the structure loads we might have are point load in columns, for example, like that. So point load, and we might have line load from a wall or something, and we might have distributed load from a floor. Okay, the type of footing we have. The types of footing we have: shallow foundation and deep foundation. Shallow foundation means footings or foundation rotting founded near the ground surface. Depth to width is less than 2. Deep foundation that applies the load to deeper strata or layers of soil. Depth to width is more than 5. Okay, there is no universal agreement for that or no formula, but just from experience. Okay, so we have shallow foundation, for example. This is our footing very near to the ground. We might also have deep foundation, so we have piled or deep footing. Okay, in this deep footing, the load is transferred to a very deep layer, strong layer, maybe sand or rocks. Okay, so this week or this lecture, we are talking about shallow foundation. Types of shallow foundation are bed footing, or in some books or standards called isolated footing. We have combined footing, which has like combining two or more isolating footing, strip footing, and raft or mat footing. Okay, this example of bed footing or isolated footing. So, for example, if you have a column like that, so the column is supported by one footing like this. Okay, this uh, an example of the combined footing. If you have two intersected bed footing, so it can have like, for example, two columns. So this is an example of the combined footing. Okay, this is an example of a strip footing under wall or uh, something like that. So you have a long footing like that, and then you have your wall on top. So the wall is continuous, and so also the strip footing. And this is an example of raft or mat footing. So as you can see, there is a slab or something like a slab, and on this slab you have multiple columns, not only one or two columns. So this is called mat or raft footing. All the footings, most of the footings are from reinforced concrete, but sometimes it can be unreinforced as well. But mostly all the footings are reinforced concrete. Okay, here is our main topic, the design of shallow footing. We have two methods or two procedures of designing a shallow footing based on bearing capacity or bearing strength. Number two is based on soil reactivity. Okay, the soil activity in some soil types with problems or problematic soil. So the soil activity is not used for all, but some soils with problems. Okay, such as expansive soil or swelling soil. Okay, so this is generally what is the design criteria for shallow foundation or shallow footing. Okay, so let's start about talking about designing of shallow foundation based on bearing strength. What is the bearing strength? The bearing strength or bearing capacity, we give it the symbol Q. So the bearing capacity is the maximum pressure the soil can sustain before failure. So the capacity is max stress can be sustained by soil. Okay, and the stress is equivalent if we give the stress sigma. So stress equal to load over area. Okay, so this is the general formula for the stress, load over area. And the load, let's say W, and the area is A. So for example, if you have this type of footing or foundation, bed footing or isolated footing, so the stress underneath here, sigma, sigma equal to the W over A, where A is the area of footing, W is the load on footing, and sigma is the stress underneath the footing. Okay, so this is the equation or the formula we are using. For example, if you have, this is our footing in plan. So this is our footing in 3D. So if this B and this is A, so the area is A. Okay, so this is the stress we are looking at, and we have some parameters we need to know. So we got the stress equal to W over A. So this stress, to be safe, we need to have to know some parameter of the soil. The bearing strength, Q. The first one for the bearing stress is the ultimate bearing strength, Q ultimate. The second is safe bearing strength, Q safe. And the third is allowable bearing pressure, QA. Okay, so in design, we have three parameters we need to know. What is the definition for this parameter? The ultimate bearing strength is the soil at the point of failure. So this is the ultimate or maximum stress can be sustained by soil at failure. So this is our first one. Second one is safe bearing strength of soil. The safe bearing strength Q safe is the safe stress can be sustained by soil, which is after applying a factor of safety. So we can remove safe and call it reduced. So safe, Q safe is reduced ultimate strength that can be sustained by soil after applying a factor of safety. The last parameter we need to know is allowable bearing pressure. The allowable bearing pressure, QA, the allowable bearing pressure, QA, is the pressure accounting for settlement that may happen to soil. And this usually in sand soils. Okay, so QA is accounting for settlement, usually in sand soil. Okay, because in some soil, like sandy soil, what happens underneath the footing? The soil may settle a little bit. Okay, so we need to allow for soil settlement. Then we reduce the bearing strength of soil. Okay, so these are important parameters we need to know for bearing strength. So let's go in depth in the terms we have for bearing strength. Q. And the bearing strength Q, we need to know how much is the factor of safety we use for soil. So Q safe equal to Q ultimate, the ultimate bearing capacity. over the factor of 50. The factor of 50 in soil is equal to 2 to 3, which is different when compared to other material like steel and timber and concrete because of the uncertainty of soil. Okay, so the factor of safety will be between 2 to 3, which is different from other material factor of safety. Okay, here also in this slide we have some general value of Q safe based on soil types. Again, this is general or generic information and need to refer to standard or other books to find accurate values. So, for example, dense gravel Q save is more than 600 kBa, loose gravel less than 200 kBa, clay between 500 or 150 to 300 kBa, soft clay less than 25 kBa, sand from 50 to 100 kBa, where kBa is equivalent to kilonewton per square meter. Okay, and now here is some or explanation of the failure modes of soil when designing under using the bearing strength procedure. So the failure modes are general shear failure or bunching shear failure. Okay, general shear failure is expected with strong or stiff ground. In this type of failure, the soil underneath the foundation or the footing pushes this soil, so this soil is going up a little bit. Okay, and this is called general shear failure. The bunching shear failure occurs when the soil is soft or compressible. So in this failure, the soil underneath is very weak, so its excessive settlement happen underneath the footing. Okay, and this soil layer cannot be used for foundation. So in this case, we might need to use deep footing or pile to transfer the root to strong layer of soil. Okay, and the most analysis usually assume general bearing failure or the first one. So this is a special case or not the common case. So the analysis assumes the general bearing failure. Otherwise, we will need to use another technique of design. Okay, so now we shift to the bearing capacity equation, Q ultimate. So Q ultimate equal to C dash in C gamma Z in Q 0.5 gamma times B times N gamma. So this is our formula for bearing or ultimate bearing capacity, where Z is the depth of footing and embedment, B is the breadth or width of the footing, and NC, NQ, and N gamma are coefficients that can be obtained from tables or calculated using a range of equations depending on phi, which is the friction angle, Okay, and C, as you know, is the cohesion soil. Gamma is the unit weight of soil. Okay, and as we can see in this formula, we have three terms. The first term is called the cohesion term. So this is the contribution of cohesion, and this one is the storage charge term, and this one is the unit weight term. Okay, so let's go deeper in the equation. Before we go deeper, just need to explain here somewhere B and D. So if this our footing at slide here. Okay, so now just explain the parameters we don't know. So here, if we have the footing somewhere here, and this is the ground level, and this is our footing or bed footing. So B is the width of the or the breadth of the footing. So this is B, the breadth. And what is Z? Z is the depth of the bed footing from the ground surface. So this is Z or Z, and this is B. So Z is the depth of footing embedment in the soil, not the footing depth. Okay, so it is not the footing depth. And again, B is the breadth of the footing. And as you can see, the Q ultimate is proportional to B and D, the breadth and the embedment. Okay, so the next slide is how to find the parameters or the coefficient in C, in gamma, and in Q. Or this can be called Terzaki coefficient. This Terzaki coefficient can be calculated using equation or using this chart. So in this chart, we can find in C, in Q, and in gamma. So in this chart, as you can see, we have phi or friction angle on the y-axis, and we have values of NC and NQ and values of N gamma on the horizontal axis. So using phi, for example, if we have phi equal to 30, so you go horizontally like this. So you will cut these three charts or three curves. The first curve in C, if you go down like this, so you can find the value of NC. So for example, NC equal to 38. Here you can find, if you go down NQ. So here the value of NQ, which is almost 23, so 38, 23. And if you go down from N gamma, so you'll find that N gamma equal to 20. Okay, so to get into this chart, find the parameters NC and NQ and N gamma, you need to know the friction angle phi of the soil. Okay, here we have an example to calculate the Q safe value for the foundation in the picture below. The foundation is clay with C equal to 10 kPa, phi equal to 28 degrees, gamma equal to 15 kilonewton per cubic meter, and the factor of safety is 3. So we need to find the Q safe value according to this given information. Okay, and we have assumption that there is no water table here to the foundation level. So here is our footing. So our foundation level is at 2 meters from the ground surface, ground level, and the plan is footing 2 by 2 meters. So from the given information, we have B equal to 2 meter and Z 2 meter. So this is all the information we got. So now we can start solving this example. So as you can see, the equation we are using is this equation. The ultimate capacity Q ultimate equal to C dash NC gamma Z NQ 0.5 gamma dash B in gamma. So we know Z equal to 2 meter, B equal to 2 meter. Okay. So what is, and also we got C 10 kBA, gamma is 15 kilonewton per cubic meter, and because there is no water, so gamma equal to gamma dash equal to 15 kilonewton per cubic meter. Okay, so what is else we don't have at the moment, or we need to calculate? We need to find what is in gamma, what is in Q, what is in C. So we will get this value using this Terzaghi chart. Okay, using phi 25, 28, 28 mark, 28 degrees. Okay, so sorry, yeah, so we have 28 degrees. So if we go to our chart here, so this is the point of phi 28 degrees. So if we go horizontally, we'll cut the diagram in these 3 points. So here is the 3 values we are looking at. This is the value of N. The first one is the value of NC, which is 32. Second value is NQ, which is 18. The third value is 15 in gamma. And when you use the table, we are looking to the closed values. So if it is not very accurate, it's okay. Just try to calculate it or get it from the diagram as accurate as you can. So it might be slightly different from my calculation or your calculation, so it doesn't matter. But at least we are close. Okay, so now if we look at the equation, we have get all the required parameters. So the equation will be 10 times 32 plus 15 times 2 times 15 plus 0.5 times 15 times 2 times 15. So we get the value of Q ultimate as 1085 kVA. So Q save equal to Q ultimate divided by FOS or the factor of safety. So it will be 1085 divided by 3 give us the value of 361 kVA. This is the value of Q save. So we find the Q save value as 361 kVA. Okay, this is a straightforward example to apply in the formula. And now we continue in the procedure of shallow footing design. The shallow footing design is a trial and error process. So if you have a load on a column, for example, and you need to design or get the dimension of this footing. So in this case, the dimension B and the other dimension A are missing. So you might have the load, but you don't have the foundation or the footing dimension. So that's why it's a trial process, trial and error process. Any design is a trial and error process. So our first step will be starting with a set of trial dimensions. It's like assuming a value of B and A, the dimension of the footing, and then calculate the safe bearing capacity, Q safe, and check with the requirement. If it is okay, this means that the stress we have, this means that, let's write it here. This means that the stress we have, for example, underneath here, which is sigma. So if sigma less than Q safe, so our design is okay and the design is final. But if sigma more than Q safe, so this means the design is not okay and you need to repeat the process again with different set of measure of dimension. Okay, so if it is okay, no problem, the design is finalized. But if it is not okay, so you need to try a different set of numbers. Okay, so this is briefly the design process of bed footing or shallow footing. And here we have another example or another class activity to calculate Q save for this footing. So if we have this footing, we have the soil probabilities of this layer are C 10 kVA, phi 25 degrees, gamma is 15, and FOS is 2. And again, we don't have water table here. In this example, we have B again 2. We don't need this the dimension in the other direction, and Z equal to 2 meter. So you should have done this yourself, but because it's the recording of the session, so I will do it for you. So again, the equation we have is U ultimate equal to C dash in C plus gamma Z in Q plus 0.5 gamma dash B in gamma. Okay, so again, what we know from this formula is C dash 10, gamma 15, Z2, gamma 15, V2. So we need to find these three parameters using this chart and phi equal to 25 degree. So here is a point of 25 degree. We cut the three diagrams in 3 points and we go vertically. So NC 26, NQ 14, and N gamma is 10. So Q, if we substitute in the formula, we will find that Q ultimate is 830. So Q safe equal to Q ultimate divided by factor of 50. So we will have a value of 450. Okay. So this is how to use the bearing capacity or bearing stress equation in the design, and that is the final part of our first topic, design of shallow footing based on bearing capacity. And here we will summarize what we have done. So we have talked about different types of footing, so different type of footing like bed footing, combined footing, strip footing, and mat or raft footing, and different design principles of shallow foundation, which include design based on bearing capacity, and the other one will be this is the first one, and the other one is based on soil reactivity. And also we learn about how to calculate the bearing capacity. So the bearing capacity equation Q ultimate again equal to C dash in C plus gamma Z in Q plus 0.5 B in gamma. And we know about Q safe equal to Q ultimate over a factor of 50, which is between 2 to 3. Okay. And also we know how to design based on bearing capacity and with a trial and error process. And uh, we design based on a set of dimension, and then we check what happened to this dimension, what if it's safe or not, and then we, if it's safe, so finalize the design. If not, so we repeat with a different step. Okay, I think that's it for the first topic. Thank you, and next topic will be design based on soil reactivity for problematic soil, such as expansive or swelling soil. Okay, thank you.